So remember, a hash map existed to provide us constant time access of arrays by using keys of our own, keys that are meaningful to us in the application. We can do all the single entry operations in asymptotic time, constant asymptotic time, just as we can do in an array. But this time we use keys of our own to refer to those values. We don't have to keep track of the array indices anymore. HashMap keeps track of them for us. This is why HashMap existed. This was its chief power. This constant time access relies on no collisions, or rather collisions within limits in each specific bucket. There shouldn't be a large number of collisions. And that relies on these two things. We have to have a hash code that distributes the keys evenly across these buckets so that there won't be an indefinite number of collisions in one specific bucket. And the hash map should adjust the table length as the hash size increases. HashMap has to have a feasible mechanism for that to make enough room when there are more and more entries. When we have these two, the size of each bucket is within a bound limit, and that's constant time access. We won't go into any such details, but there are proofs of this in theory books, textbooks. When we have these two in place, the possibility of the worst case that a large number of majority of the entries going to one specific bucket is negligible. It just doesn't happen. So the key hash code should be distributing the key objects evenly to the buckets. For that, it should be generating distinct values across unequal objects that are not equals of one another. Not only that, it should disallow common bit sequences across the objects, across the unequals objects, especially in the low order bits. Remember, the low order bits are looked up when the keys are mapped to the buckets. The high order bits are masked out depending on the table length, current table length. So for instance, if your hash code is always returning odd values, bit sequences ending with 1, then you're only using half of your hash capacity. The possibility of collisions is doubled. So how to implement the hash code? The key hash code is crucial for the performance of your hash map. How to implement it? The answer to that is use your IDE for it to implement hash code and equals. It does them both. Your IDE would implement hash code and equals on the fields you tell them to. And it does a very good job on that. This is the Eclipse implementation. I don't know what IntelliJ does. I'm an Eclipse person, but I'm sure it does a very good job on that as well. So just use your IDE and don't even look back. It will do a very good job on it, and very nicely too. We won't get into this implementation at all. It just isn't worth the time. But just for some awareness, just to gain some insight, out of curiosity if nothing else, let's spend a moment here. This hash code is implemented on these 3 fields of the object. This is the formula, the calculation. This is what's going on here, the one I put into comment. The best way of looking at it is looking at it as how each of these 3 values, field values, is going into the 32-bit sequence. Your hash code is an integer sequence, 32-bit integer sequence. So how each of these values is reflected into that sequence. First of all, if you just plain edit these three as is, if you just edit them up, then every combination of same one specific set of values across these fields would generate the same hash code. 1 plus 2 plus 5 is the same as 2 plus 1 plus 5. You wouldn't want that. So put each of them into different portions of the 32 bits. Here, first is going to one portion. Second, the value of second field is going into another portion, and so forth. The multiplication in the broad sense is shifting to the left. But then don't just shift them as is. Here, for instance, if they were multiplied by 32 instead of 31, then they were just shifted as is 5 positions to the left. 32 is shifting 5 positions to the left. In that case, if, for instance, on two different objects, if the value of these two first and second fields remained the same but third only changed, then the low end bits would be the same on these two objects. You don't want them either, so don't just shift them, but also change the bits around. Multiplying by 31 is a sequence of all ones. When you multiply a value by a number like that, you're tampering with every bit. Every bit is touched. Not just that, there are carry bits. It's propagating to the left, high end. A good hash function breaks all the patterns there are. So much so that there isn't any way to trace back the values going in just by looking at the results, or a number of results, large number of results. Like, you can't even vaguely see some patterns in the values going in. It's because the hash, they are well hashed, they are well dispersed. Any pattern in these values going in do not reflect to the result. This is a good feasible hash function. It isn't the best there can be, but it is definitely a good feasible one. Feasible here in terms of the computation time. This is from the C++ times, if I remember correctly. This multiplication by 31 is definitely from C++, so it's being used just about forever. Java is using it. This is the hash code of string class. It is the exact same logic here, except for this constant in the end. It is doing it, applying it on the characters that constitute the string in place of the fields of the object. So your IDE would do all of these. All there needs to be done would cover everything, and very nicely too. Just put your IDE at work for implementing hash code, and along with it equals. It will do a very good job. They'll be in safe hands. So we now have a good hash code to distribute the keys evenly to the buckets. But then we have to have enough number of buckets. We have to give enough room for the keys to go in so that there won't be many collisions. The question here is, when would be a good time to increase the table length, the capacity, the hash capacity here, or in other words, the number of buckets, number of cells of the hash table. When would be a good time to increase this capacity? The answer that HashMap has lies in this load factor. Load factor represents the fullness of the hash map currently. How full is your hash map? It is a ratio. It's the ratio of the number of entries currently sitting in the hash map over the capacity, total capacity. So if for instance your table length is 12 or 16 rather, it has to be a power of 2. There are your current capacity is 16 and there are 12 nodes in the hash, so the fullness is 75%. In the default setting, every time your hash map is 75% full, every time it hits that limit, that load factor, then it adds another size like that to itself. It doubles the size. In threshold here, you'd also see it as a field if you go into the hash map code, source code. These fields are not public. Threshold is the exact amount, the exact fullness limit dictated by the load factor. You'll also see that in HashMap. The load factor is constant throughout the lifetime of a hash map. It never changes, it's fixed. Once constructed, it is there, carved in stone. The hash map is always resized up to a power of 2, to the smallest power of 2 that can accommodate the current number of entries in the hash map. It is never sized down, like you can clear the entries. The buckets can be null, however the table remains as is. It does, the capacity never goes down, no matter how long, what the length of the table is. We'll see all these in the code when we experiment. Before we proceed, let's just pin these down with a specific example. In this case, currently, this is the table length. We have 1K buckets in the table, that's 210. The load factor is the default, 75%. So the threshold is 3/4 of 1K. And we have 768, the exact same value as the threshold. That's the number of entries currently in the hash map. We put, after that, when we have that, this is the case, this is the situation, we add one new value. The size went up, we exceeded the load factor, so the hash is resized. It now is, the size is doubled to 2 to 11. New threshold is likewise, it's doubled, it goes with the capacity. Load factor is the one telling all these, telling when to resize. It never changes, it only dictates when to resize. So in this case, for instance, the put operation to place the entry that goes beyond the threshold is a linear operation. Your constant time put operation turns into a linear operation. and you hit the threshold.